The implicit survey.
So for this and this, right?
Yeah.
So I'm going to do one, right? I'm going to choose CQ1 contains CQ2. So this means I pick up F1, F2 from CQ1. We're going to show that this pair also is CQ2. That's it. Right? Okay. So once I have this, so remember, this is the boundary value of the VW, right? VW. So the relation between these is that because this equation is equivalent, so once I have a solution, so this is correspond to certain solution, VW and VW will give this, right? So this solution, VW, will correspond to a potential function in U in the equation, right? I know this is true from our reduction. Okay, so therefore, so they exist, the U1, okay, satisfy the connectivity equation. Okay, and such that the square root of R d U1 du2 du1 bar is equals to restriction on boundary is equals to F1 and F2. Okay. Okay. And now you can see from here, you can easily see, you can solve for du1. So this one implies that du1, d bar u1, okay, so this thing is equals to r negative 1/2 f1, f2, okay, r1. So this is coming from the single function u1. But from this relation, you can see that since I know that there's the Newman map, so of course I know this. Because everything here is on the boundaries, okay? On the boundary. So I know this value. And also I know F1, F2, because F1, F2 is given here. Of course I know. So therefore I know the boundary value of du1, du2. I know that. Okay? Alright, so from here I'm going to I'm going to solve the following kind of gradient. I'll look at the second connectivity equation. Gradient R2, gradient U2 is 0, and the U2 on the boundary agree with the U1 on the boundary. So here I know the U1 of course, U1 on the boundary, okay, and I use this existing boundary data to compute the second connectivity equation to get solution U2. Okay? Then you can see that from here you can see that since the boundary, since the derivative Newman map is equal, so this condition will imply that the square root of R du2 dn is equals to, so this is R2, okay? So should equal to square root of R1, then du1 dn. Right? So this is defined to be the square root. So this to the map equals, that means this. Okay. So what does it mean here? What does it mean? This means that this is the normal derivative, right? And here, the tangential derivative is determined just because the functions along the boundaries, right? So that's the things I know. So from here, I can determine they agree with in any tangential derivative they are equal. But here, the Newman map tell you that the normal derivative also equal. So what does it mean? It means the gradient also agree on the boundary. So in particular, this implies that, and also R1 and R2 agree. So I can basically change these two. So this implies that d bar u2 or d bar du2 d bar u2 is equals to d u1 d bar u1 on the boundary. Right? Now this one, d bar u2 and d bar u1 agree with this, okay? Then you multiply this with the square root r. Square root r is also agree, so they are still equal, right? Now this, once you multiply square root r, you can see this is basically become f1 and f2. I mean declare f1 and f2. So this f1 and f2 turn out to be agree, corresponds to the potential that is correspond to second kind of limits. So this means that so this will show that the same f1 and f2 has to be C2. So the key is here this relation for give you the final result. So this shows that if you pick up our R2, f1 f2 in CQ1, then this one has to be CQ2. And vice versa. So this CQ1 and CQ2 must agree. Okay. And then from here, you can, so the remaining step is to go from, how do we go from here, step by step, to recover Q. Okay. So once we recover Q, R. So any questions? So this is what we expected to do today. And we made the final reduction and reduced the use to go back to the flush data.
All this type of problem I have some originally take from Caloron's potential equation. Now, since that deals physically with capacitors and resistors, is there like, can you use this type of equation in other physical form besides
Yeah,
just
I mean, so this is the kind of big equation, right? So this is it has a physical problem. Right? Then this equation is somehow equivalent to Schrodinger equation. This is called scattering theory. In the scattering theory, there are big field. And also it will be connected to the equal spectrum theory. I mean, equal spectrum theory, you know what I mean.
So when we're talking about scattering and spectrum, we're talking about atomic level, electron levels, but
well, there's a lot of other
spectral theory
related things like potential. I mean, here you can have vector potential, or you have Maxwell equation, or elasticity system. They're all related to the same thing.
So when you talk about spectra, I think